We are in Chapter 7, Techniques of Integration, Part 1. Chapter 7 is getting split into two parts. Part 1 is going to be on our Unit 1 exam, and Part 2 will be on our Unit 2 exam. So 7.1 is integration by parts. The technique of integration by parts allows us to reduce a complicated integral to a simpler integral. The rule that corresponds to the product rule for differentiation is called the rule for integration by parts, or just simply parts. The product rule states that the derivative d dx of two functions being multiplied together, f of x times g of x, is equal to f of x times the derivative of g of x plus g of x times the derivative of f of x. Using definite integrals, the equation becomes, and so if we have integrating both sides, we're going to end up with f of x times g of x is equal to the integral of our right side, which is f of x, g prime of x, plus g of x times f prime of x dx. And using our integration properties, we know that this is the same thing as our left side staying the same, but the integral of each of these terms by itself, so the integral of f of x, g prime of x dx, plus the integral of g of x, f prime of x dx. And rearranging our terms and going ahead and isolating the integral of f of x, g prime of x dx. We have f of x, g of x, minus the integral of g of x, f prime of x dx. And so the above equation is the formula for integration by parts, which is what we're talking about in this section. It is easier to remember in the following notation. So we're going to let u equal f of x and v equal g of x. Then du is going to be the derivative of f dx, and dv is going to be the derivative of g dx. So integration by parts, rewriting that exactly what we wrote up above in terms of f's and g's as the integral of u dv is equal to u times v minus the integral of v du. So definitely a formula that we need to know, very useful for Calc 2. So conditions for integration by parts. The integrand can be written as the product of two factors. So the integrand needs to be written as two factors that we're going to call u and v. And it's possible to integrate dv to get v and differentiate u to get du. The integral v du can be found. The example at the bottom of page 1 says find the integral of x e to the negative 2x dx. And if you were to try this using u substitution, which was a method that we learned back in Calculus 1, the best thing to do is first try to integrate with just the basic rules that we've had, then try u substitution, and then try integration by parts. We will discuss in class some ways to recognize when to use what method. And so for this problem, we're definitely going to be trying integration by parts. And using parts, we're going to let u equal something and then also dv equal something from our problem. And the best thing to pick for u is going to be the polynomial, which is easy to take a derivative of, and it actually gets, in a sense, smaller and easier to deal with. So if you look at our polynomial here is just x. And so if I let u equal x, that means that dv would be the remaining part of this problem, which is going to be e to the negative 2x dx. So from u, I'm going to take the derivative. So du dx is equal to 1, or just du is equal to dx with that differential. And then integrating the second part, I'm going to end up with the integral of dv is just v, and then the integral of e to the negative 2x with respect to x is going to become negative 1/2 e to the negative 2x. Yes, we typically would put a plus c. However, my final answer, I still need to integrate, and I'm going to put that plus c, that constant, at the very end. So the formula that we have is right above this, and I'm going to go ahead and copy that down. It is the integral of u dv is equal to uv minus the integral of v du. And so from here, I'm just going to substitute everything back in using the original variable, which was x. So for u, we had x. V is negative 1/2 e to the negative 2x minus the integral of v du. And so v is negative 1/2 e to the negative 2x. And then du is the same thing as dx. I'm going to clean it up a little bit before I integrate. So this is negative 1/2 x e to the negative 2x. I have a negative and a negative, so that's going to become positive, and I can pull that 1/2 out in front. And then I'm going to integrate e to the negative 2x dx. The rest of the problem stays the same, except for the integral part, which I need to integrate. So I have negative 1/2 x e to the negative 2x plus 1/2, and then integrating e to the negative 2x dx, we arrive at negative 1/2 e to the negative 2x. And since I'm done integrating this problem completely, I am now going to add my plus c, my constant term. I'm going to clean this up just a little, and I have negative 1/2 x e to the negative 2x minus 1/4 e to the negative 2x plus c. So this will be our final answer. You are able to check your answer by taking the derivative of the solution that we got for this one. And if you have enough time, you can do that, especially on an exam or on a quiz. At the top of page 2, we have another problem which says find the integral of ln of x dx. We're stuck here. We do not have a solution from all the formulas that we learned about integrating for the integral of ln of x dx. And using u sub, you would arrive at being stuck on this one also. If you let u equal ln of x, you wouldn't be able to go much farther with that problem. So we're going to try integration by parts. So we're going to let u equal, and we're going to let dv equal. U must be ln of x because we don't know how to integrate that, since that's our problem that we're dealing with here. So I'm going to let u equal ln of x. That means the leftover part here is just dx. So I'm going to have dv is equal to dx. So we're going to take the derivative of u with respect to x, and you'd have du dx is equal to the derivative of ln of x is just going to be 1 over x. So du is equal to 1 over x dx. And then here we would integrate. So the integral of dv is v, and the integral of dx is x. And I'm going to go ahead and write down the formula again for integration by parts. So we have the integral of u dv equals uv minus the integral of v du. From here, I'm going to substitute in what we have expressed over on the right side of this box, and they're going to be in terms of all the x's. That was our original variable. So u is equal to ln of x, v is equal to x, minus the integral of v du, so v is x, and du is equal to 1 over x dx. From here, I just need to clean this up a little bit, and I have x ln of x minus our x's here would reduce out, and we'd have the integral of dx. So x ln of x would stay the same, and then integrating dx is just x. And since we're dealing with indefinite integrals, again, I'm going to add that plus c at my final answer. So again, to check your work here, you could take a derivative of this to see if you did this correctly. The next example says, find the integral of 3x squared plus 4 times e to the 2x dx. Again, like the first example that we saw, we have a polynomial times an exponential, and so that leads me to thinking that I would have to use parts. Again, you should always consider using u substitution first, and then if that doesn't work, then you would try integration by parts. So if we use integration by parts, I would have to let u equal something and dv equal something. And again, u, I'm going to let that be my polynomial here, which is 3x squared plus 4. And then dv is the rest of this, which is e to the 2x dx. From here, I need to find du, and du would be equal to the derivative of 3x squared plus 4, which would be 6x dx. And then I'd have to integrate dv, which is v, and then integrate the other side of e to the 2x dx, which is going to be 1/2 e to the 2x. Again, we're not yet putting that plus c. We will do that constant at the very end. Using the integration by parts method, we have the integral of u dv is equal to uv minus the integral of v du. And then substituting in what we had obtained in the right of that box, I have u, which is 3x squared plus 4, times v, which is 1/2 e to the 2x, minus the integral of v du. And again, v is 1/2 e to the 2x, times du, which is 6x dx. From here, I can simplify this a little bit, and I'm going to go ahead and zoom in here a little bit so my writing's a little bit more clear. But from here, I would have 1/2 e to the 2x times 3x squared plus 4. And then I have minus, and I have a 1/2 and a 6, which is 3, so I can put that in front of my integral. And then I have the integral of x times e to the 2x dx. So the integral that I have here, unfortunately, I am unable to integrate it as it's written. It looks very similar to the first example that we did on the previous page. And so I'm going to go ahead and use integration by parts again. So yes, you are able to use integration by parts multiple times. I am just going to be integrating by parts the integral that we have here, and the rest of that expression is going to just move on down with it. And so I would let u equal, and I'm going to also have to let dv equal something. So u, again, is going to be my polynomial, just x. And then dv would be the remaining part of this, which is going to be e to the 2x dx. So then taking the derivative again, du would be dx. And then integrating both sides of this, I get v equals 1/2 e to the 2x. So from here, everything is going to come down, and then I will use integration by parts again. So I have 1/2 e to the 2x times 3x squared plus 4 minus 3 times, and then using integration by parts, we have the formula up here. And so I'm going to have u times v. So I have x times 1/2 e to the 2x minus the integral of v du, which is going to be 1/2 e to the 2x dx. From here, we're going to distribute the negative 3 to both of these terms, and then we're also going to integrate. So we have 1/2 e to the 2x times 3x squared plus 4 minus 3 over 2 x e to the 2x plus 3 over 2, and then integrating e to the 2x, that's going to become 1/2 e to the 2x. And I'm going to go ahead and put my plus c since I'm done integrating. From here, I can simplify. I'm going to distribute the 1/2 e to the 2x, and we have 3 over 2 x squared e to the 2x plus 2 e to the 2x minus 3 over 2 x e to the 2x and plus 3 over 4 e to the 2x plus c. From here, we can combine some like terms. And so I have a 3 over 2 x squared e to the 2x. And then we have a minus 3 over 2x e to the 2x. And then I can combine 2 e to the 2x and 3/4 e to the 2x. So this would be combining 8 over 4 plus 3 over 4, and we get 11 over 4 e to the 2x, and then plus c. So using integration by parts twice for this problem, And you could, this is usually the most that we will do integration by parts. There's also another method of integrating by parts when you have to do this more than once, and it's using a table method. So the next example that we have says find the integral of sine inverse of x. So we cannot integrate this, and this problem doesn't have much to it. So using u substitution would definitely not work. So I'm going to try integration by parts. So I need to let u equal part of this and dv equal part of it also. So u would have to be the inverse of sine. So I'm going to go ahead and let u equal sine inverse of x. And then dv is going to have to be what's left over, which is just dx. So taking a derivative of sine inverse of x, that's going to be du is equal to, and we have 1 over the square root of 1 minus x squared dx. Make sure you go back and look at your inverse trig functions, the derivatives of those, and if you don't know them well, then definitely study those. We then are going to integrate the second part, and so we get v is equal to x. So from here, I'm going to go ahead and use my integration by parts formula, which is the integral of u dv is equal to uv minus the integral of v du. And so substituting in these parts, we have u, which is sine inverse of x, times v, which is x, minus the integral of v, which is x, times du, which is 1 over the square root of 1 minus x squared dx. And from here, I am stuck on my integration. I have an x and then also a radical 1 minus x squared. So I am unable to integrate this, and again, do not jump automatically to using integration by parts. First thing to think about is, do you have any kind of formulas? If that doesn't work, then the next thing you should consider is using u substitution to integrate. So if you think about using u substitution, I'm going to try it, and if it doesn't work, then I can redo something else. Now, instead of using a u, I'm going to let w equal, since I've already used u and v up above. You can always leave it, but it does get kind of confusing when you're starting to call different things by the same variable. So I'm going to let w equal 1 minus x squared, and then dw would equal negative 2x dx. And this works out really nicely since I do have an x and a dx left over. So from here, I have x times sine inverse of x minus, and then using my u substitution, I'm going to have the integral of, and I have a negative 1/2, and it's going to be times 1 over the square root of w dw. And cleaning this up just a little bit before I integrate it, I have x sine inverse of x. This is now going to become plus. I'm going to pull that 1/2 out in front of my integral. And then I have w raised to the negative 1/2 power dw. This is a nice problem to now integrate. Just remember that your original variable was x, and right now I have an expression that's written in terms of x's and w's. So I have x sine inverse of x plus 1/2 times, and I'm going to add 1, divide by that same value, so I get w to the positive 1/2 times 2 over 1. I'm going to go ahead and throw my plus c here. From here, I can clean this up. I have x sine inverse of x. My 2's would reduce out, and I have plus the square root of w plus my constant c. From here, I'm going to back substitute in what w was defined as, and I have x sine inverse of x plus the square root of w, which is right up here, which is 1 minus x squared plus c. And this would be my answer. And again, hopefully you can see that calling it W allowed me to back sub it in a lot easier than if I had called it U and got confused on which U I was talking about. So on the next page, we have another example that I'm going to go ahead and circle, and we'll work on that one together in class. And then the next part says we can combine the formula for integration by parts with the fundamental theorem of calculus to evaluate definite integrals by parts. So same idea, but this time we're going to be using that fundamental theorem of calculus to evaluate. So evaluating it from the lower limit of A to the upper limit of B. So from here, the next example says find the integral from 1 to 2 of x squared ln of x dx. So this time we see that I have a definite integral, so I need to be evaluating this and getting a numerical answer. And so looking at it, trying to use substitution, you'll realize that you do get stuck with using that, as if you let u equal ln of x. When you take the derivative of that, you get 1 over x dx, which you would still be left over with another x term. So I'm going to try integration by parts. So I'm going to let u equal something and dv equal something else. So for this problem, in order to set this up, I realized that ln of x would have to be set equal to u. And we did a problem earlier in this section where we had to integrate ln of x dx. And so for this, that would have to be my u, meaning that I am left over with x squared dx. So from here, I'm going to take the derivative of ln of x, which is 1 over x dx, and then integrate, and I get v equals 1/3 x cubed. Then using integration by parts, have the integral of u dv is equal to uv minus the integral of v du. And I'm just going to substitute in what I have. So u is equal to ln of x, and v is equal to 1/3 x cubed minus the integral of v 1/3 x cubed du, which is 1 over x dx. So the difference between this and the previous problems that we've done is that this is a definite integral. And so we should be adding in to evaluate this from 1 to 2. I want you to notice a couple things. First is that this expression that I have right now is in terms of x. So it's not like u substitution where we had to change those limits of integration when we had a definite integral. And so you are definitely able to add in the from 1 to 2 and then from 1 to 2 here. I usually don't write it just because it gets so condensed and so messy. And I will wait until I'm done, and normally when I would have been done if it was an indefinite integral, and then I will evaluate the whole thing from those values from 1 to 2. So that's what I'm going to do, but feel free to integrate parts of it and evaluate parts of it as you go. So the next thing is I'm going to clean this up a little bit, and I have 1/3 x cubed ln of x minus, and this is going to simplify the 1/3 I can pull out in front, and then I have the integral of x squared dx as that simplifies. And then I'm able to integrate this, and so I have 1/3 x cubed ln of x minus, and then I have 1/3 times 1/3 x cubed. And then again, I normally have a plus c, but I'm not going to do that this time. I'm going to say evaluating from x equals 1 to 2. I'm going to clean it up first, and then I will evaluate this. So I have 1/3 x cubed ln of x minus 1 over 9 x cubed, evaluated from x equals 1 to 2. And so using that fundamental theorem of calculus, I'm going to evaluate that upper limit first. So I have 1/3 times 2 cubed ln of 2 minus 1 over 9 2 cubed minus, and then I'm going to substitute in 1. So I have 1/3 times 1 times ln of 1 minus 1 over 9 times 1/3. And we know that ln of 1 is just 0. So from here we can clean this up even more to arrive at a final answer. So this is going to be 2 raised to the 3rd is 8. So we get 8 over 3 ln of 2 minus 8 over 9. And then the next term is just 0. So I'll say minus 0 since I could distribute that negative in. And then minus negative 1/9 would be plus 1/9. And so this is going to work out to being 8/3 ln of 2 minus 7 over 9. The problem at the top of the next page says find the integral from 1 to the square root of 3 of arctangent 1 over x dx. So first thing I notice is that I am unable to integrate this, and I am stuck on using u sub. So definitely I'm going to try integration by parts, and using integration by parts I have to let u equal the arctangent of 1 over x. And that means that dv, the other part, is just going to be equal to dx. So then du is going to be equal to, and then with arctangent of 1 over x, it's going to be 1 over 1 plus 1 over x squared, and then times that derivative of 1 over x, which is going to be negative 1 over x squared, and then dx, and then integrating dv, we end up with v is equal to x. So using our integration by parts formula, which is the integral of u dv, we have uv minus the integral of v du. And from here I'm going to substitute in everything that we have. So our u value is arctangent of 1 over x times v, and v is just going to be x. So then we have minus the integral of x times 1 over 1 plus 1 over x squared times negative, I'm going to pull that negative that we had out in front here, make this a positive, 1 over x squared dx. I'm going to zoom in here just so my writing's a little bit clearer. But from here I'm going to clean this up, and then I'll see if I can integrate this or if I'm still stuck and have to do some more work. So first thing is that x that I have out, I'm going to put in the front. So we have x times arctangent of 1 over x plus the integral of, and then I notice that one of these x's would cancel or reduce out. So we have 1 over, and so I have an x out here times 1 plus 1 over x squared dx. And that's kind of messy right now with fraction within a fraction. So I'm going to see if I can clean that up a little bit before we actually deal with it. So x times arctangent of 1 over x plus, and then if I distribute in the x, I have 1 over x plus 1 over x dx. And still messy with that compound fraction with a fraction inside a fraction. So I'm going to go ahead and multiply both the top and the bottom by x. And that should clean this up and make it look a little bit nicer and easier to deal with. So we have x arctangent of 1 over x plus the integral of x over x squared plus 1 dx. So I'm still unable to integrate this at this time. Since we defined u up above, I'm going to let w equal, and I'm going to let that equal the denominator, which is x squared plus 1. and then taking the derivative of both sides, we get dw equals 2x dx. And from here I'm going to use my u substitution, or w substitution for this case. So I have x arctan 1 over x plus, and this time I have the integral of, and I'm going to end up with 1/2. I'll put the 1/2 out in front of the integral. And I have 1 over w dw. I want to note really quick that if you were to evaluate this integral, notice that we have x's and w, so I'm going to back substitute in once I am done integrating, and then I will evaluate it at those original lower limit and upper limits that we were given for the problem. So from here we have x arctan 1 over x plus 1/2, and we have integrating 1 over w dw, we get ln of absolute value of w. Don't need to put a plus c since I am dealing with a definite integral here. And I'm going to go ahead and back substitute in what w was so I can get this whole expression in terms of x's. So I have x arctan 1 over x plus 1/2 ln of the absolute value of w, which is x squared plus 1. And technically you don't need those absolute value lines since we are dealing with an expression that's always positive. And we're going to evaluate this from x equals, and our lower limit of integration was 1, and our upper limit was rad 3. So from here I'm going to substitute in the square root of 3. So the square root of 3 times arctangent of 1 over rad 3 plus 1/2 times ln of, we have rad 3 squared plus 1, then minus, and we're going to now evaluate this at 1. So we have 1 times arctangent of 1 over 1, which is just arctangent of 1, plus 1/2 times ln of 1 squared plus 1, or ln of 2. So from here we need to evaluate this. First thing is we have arctangent of 1 over rad 3, and then also arctangent of 1. And so to think about these, we know that with dealing with arctangent, we have to think about our tangent and the inverse of that. So I'm going to go ahead and write it as tangent inverse of 1 over the square root of 3 for that first one that we have is equal to, and I'm just going to call it y. And so this would be tangent of y is equal to 1 over rad 3, rewriting that without that inverse. And so this would be on your unit circle if you think about it, if you did times 1/2 times 1/2. So this would be the point on the unit circle where cosine is rad 3 over 2 and sine is 1/2. And that occurs when y is equal to pi over 6. So we know that we have rad 3 times pi over 6 plus, and then we have 1/2 ln of 3 plus 1 would be ln of 4. And then now we need to look at arctangent of 1. And arctangent of 1 would occur when sine and cosine are equal to one another. And if you need a little bit more help with this, you can think about it just like how we did the one up above and say tangent inverse or arctangent, and it's of 1 is equal to z. And I would say tangent of z is equal to 1. And tangent of z would equal to 1 when sine and cosine are both equal to each other, which on our unit circle occurs at pi over 4. And so we have minus, this would be pi over 4, and then plus 1/2 ln of 2. And so from here, we can simplify this a little bit more, rewriting this as rad 3 pi over 6 plus 1/2 ln of 4 minus pi over 4 minus 1/2 ln of 2. And this is a perfectly fine answer. It can be simplified a little bit more if you were to think about ln of 4, the second term that we have here. And you could think of ln of 4 as ln of 2 to the second power. And then using those properties of logs, we can rewrite this as plus 1/2, and then moving that exponent out in front of the logs using those properties, so times 2 ln of 2 minus pi over 4 minus 1/2 ln of 2. And so from here you could then combine those natural logs of 2, and so we would end up with rad 3 pi over 6 minus pi over 4, and then ln of 2 minus 1/2 ln of 2 would be positive 1/2 ln of 2. So go ahead and circle that as my final answer. So we have another example right below this, and I'm going to go ahead and circle this example, and we'll work on this one together in class. And on the next page, the example says, first make a substitution and then use integration by parts to evaluate the integral. So it says to first make a substitution. So in order to do this, I need to think about a way to make a substitution that would make sense for this. And so the problem is we're evaluating the integral from 0 to pi of e to the cosine x sine of 2x dx. So first thing I notice is that I'm dealing with different angles, cosine of x and sine of 2x. And so if you remember, I'll write it up here, that sine of 2x is equal to 2 sine x cosine x. With our trig properties, I'm going to go ahead and use that to rewrite this in terms, so that way the problem is in terms of all the same angle. So from here, I'm going to have the integral from 0 to pi of, and it's e to the cosine x times, and it's 2 sine x cosine x. I'm going to put the 2 out in front, and then we have, so times sine x cosine x and then dx. So now that we're in terms of all the same angle, I'm going to go ahead and try use substitution right now. I notice that I have things in terms of cosines and things in terms of sine, and so I'm going to go ahead and say I'll use a w, equal, I'm going to say cosine of x, and then dw equals negative sine x dx. And so now this problem is going to become 2 times the integral, and yes, my limits of integration are going to change, and I'll do that in just a sec. And it's going to be e to the cosine of x is just w. And then I have sine x cosine x, and so that's going to be negative, I'll put that out in front, and times w dw. And so from here, this looks very similar to ones that we've already done in this section. And I know that to integrate this, I will have to use integration by parts. But before I go any farther, I do need to write down, since this is a definite integral, those new limits of integration. So I'm going to substitute in that upper limit of integration into my w substitution. So this would be evaluating this at cosine of pi, and for the lower one it would be cosine of 0. And cosine of 0 is just 1, and cosine of pi is negative 1. And I am able to switch those limits of integration and also switch the sign. And so this would now become positive 2 going from -1 to 1 of w e w dw. So using integration by parts, I'm going to let u equal w, and then dv would equal e to the w dw. So du is going to equal dw, and then integrating over here we get v equals e to the w. So using our integration by parts formula, don't forget you do have a 2 out in front. So it's going to be the integral of u dv is going to be u times v. So we have w e to the w minus the integral of v du, which is e to the w dw. And then we need to still integrate this, and then we need to evaluate this from, if we're in terms of w, that would be going from -1 to 1. So we have 2w to the w as I distribute that 2 in, and then minus 2e to the w. And we need to evaluate this whole entire expression here from w equals, and we're going from -1 to 1. So substituting in our upper limit of integration, we have 1. So it's going to be 2 times 1, which is just 2, e to the first, minus 2e to the first. Then minus, and we need to substitute in -1. And so we have 2 times -1, or -2, e to the -1, minus 2e to the -1. And then evaluating this first part, we have 2e to the first minus 2e to the first. Those are just 0. And then we have -4e to the -1, or just 4e to the -1, or you can write this as 4 over e.